There we go. Good. Well, good morning and welcome. It is still just morning. What I'm going to talk about this morning is how you can use Java in this wonderfully named Internet of Things. Now, I apologize in advance because this is really rather a marketing term. I don't like to use marketing terms. I like to talk technical. But it's something that people are talking a lot about at the moment, this Internet of Things. So we'll discuss what the Internet of Things really is, and we'll talk about how Java fits into the picture of connecting all these devices. Now, let's just have a quick show of hands to start with. Who would consider themselves an embedded developer? Right, okay, a couple of people. Who considers themselves an enterprise developer? Okay, more people. And what about sort of like client desktop developer? Okay, so mostly talking to enterprise developers. That's interesting, but that's fine because that gives me an idea of where you're coming from. And as we'll see, the enterprise side of things is still just as important in terms of this kind of idea. Right, so as an Oracle employee, I am duty-bound to put up the obligatory legal slide. So I have done that. Basically says that we're not committing to deliver anything on a particular date for a particular thing, which is a little bit superfluous because we've actually released everything I'm talking about. So we won't worry about that. We'll just move straight on. Okay. Now, the reality is that right now, not much of the data that we work with is generated by machines. Most of the data that we work with is generated by us. So people generating the data. We have all sorts of things that are generating data. There's, think about uploading of photos, uploading of videos, people entering data, people generating data by swiping things and all sorts of things like that. So what we're seeing is that right now, from a machine-generated perspective, about 11% of the data that we work with is generated by machines. And if you talk to IDC, what they say is that by 2020, so about 6 years from now, that's going to rise to 40%. So that's a quadrupling, a 400% increase in the percentage of data. And if you think that the rate of data that we're generating is also increasing, almost exponentially, then we're talking about a huge amount of data. This really is going to be big data in the true sense of the word. And the reality of that is that we're going to have many, many more devices connected to the network. We'll see lots and lots of things. There are a few seats at the front here if people, if there's still room. In fact, there's quite a few seats right down at the front if you're interested. If you want to sit rather than stand, please do. So we're going to see lots and lots of devices being connected to the network. Things with an IP address or some way of connecting to the network and producing data. What this is going to do is enable us to make decisions in a much more intelligent way. So this is what the Internet of Things is all about. It's about connecting things. It's about having things not just delivering data, but also allowing control. And that's one of the things I think that gets missed when people talk about the Internet of Things, is that it tends to be viewed as more of a one-way flow. People tend to think of it as, okay, so we're going to gather data from a sensor that reads your heart, or we're going to gather data from a sensor which reads the temperature in a room, or a sensor that reads some other piece of data. So people tend to think of it as being a flow of information from sensors into the back end, into the enterprise system, the server, where we can do analytics and we can process that data and we can find interesting things. But the Internet of Things is also about data flowing the other way as well. It's about taking that information, making decisions based on it, and then controlling things. So when you've got information that's being gathered about temperature sensors, how can we use that to more carefully control air conditioning? If we measure things like moisture in a field, how can we more carefully control the amount of water that's being put on crops? Because that's where the real value of this Internet of Things comes. Because if we can analyze this data more carefully, make more intelligent decisions based on that data, we can then control things and we can reduce waste. And the reality of life, as we're going to see it in the future, is that with more and more people on this planet, we have to be more economic in terms of our usage of the resources that we have. So the more efficient we can be in using those resources, the better we can be in terms of providing for all the people that are on the planet. So this is something that actually has to be done. It's not just a wishful thinking kind of idea. In terms of what we're looking at from the Java perspective, and I'm talking about Oracle really, is a number of distinct areas. And some of these are sort of bigger than others. So there's things like home automation. You know, we've already seen things like Nest, who are doing smart thermostats. That's a really good example of how we can connect sensors and we can have finer control over the systems in order to reduce the costs, reduce the waste of our heating or lighting or things like that. So home automation. How can we monitor different things? There's an interesting company outside who are doing NFC-enabled rings, and they're showing a demonstration where you can actually get into your house without having a key. I've got to admit, I'm a little skeptical about some of the security aspects of that, but in essence, it's a key, but not using a physical key. It's using an electronic key. Industrial automation is another big thing from the point of view of looking at how we can reduce waste. If you've got a chemical plant that's processing petrol or oil or something like that, then if you can monitor many more aspects of that process, then you can improve the efficiency of how well it's working. You can reduce the waste in terms of power and so on. Smart utilities. This is something which is becoming very big here in Europe because the government is trying to meet targets in terms of CO2 emissions and reducing the amount of electricity that we use. So there's this idea that we can have smart monitoring of our electricity usage. And this kind of ties into home automation as well. So all of us at some point are going to get some kind of smart meter which enables the electricity company or the gas company to read the meter remotely. They won't have to come send somebody around to actually look under your stairs and read the numbers on the dials. They'll be able to do that automatically. But you'll also be able to see information from that. So you'll be able to go to a website, you'll be able to use a smartphone application, and you'll see details about how your electricity usage goes and how your gas usage goes and those sorts of things, with the idea that it will enable you to reduce your waste. Again, I still wait to see how that's actually going to work in practice. But healthcare, this again is something that we really have to address because the population of certainly this country is getting older. There'll be less young people to look after older people in the future. We need to find ways of reducing the amount of physical actions that are required in order to monitor and look after people. So having the ability to have sensors where you can measure blood pressure, you can measure heart rate, you can measure temperature, all of those sorts of things, and do that without having to send somebody round, without having to go to the doctor, without having to go to the hospital, that's going to really help in terms of reducing the costs of healthcare. Because if we can detect things earlier, we can reduce how much it's going to cost in terms of treating those kinds of things. And automotive, again, this is something which is right now becoming a very big field of interest. In Europe, there's now a mandate coming from the European Union which says that, I think it's from 2016, I'm not sure exactly, but I think it's from 2016, all cars are going to have a telematics system fitted to them. That means that they will have some kind of modem, sort of GPRS modem or whatever, built into them, so that in the event of an accident, the car can automatically communicate with the emergency services to alert them to that fact. So that's one thing that's being mandated by the European Union, so that every car will have that in there. And what all the car manufacturers are doing, we're saying, well, if we have to put that in there, let's see what other things we can build on top of it. So what other services can we offer that takes advantage of that? Having the car being connected to the service center, so not just, it's like healthcare, but for cars. So you can monitor what's going on with the car. If the car needs servicing, you actually can get a text message or an email saying, we've detected that your oil pressure is running a little bit high, you need to bring your car in for service. And that way you can get to it before it becomes a significant issue. Looking at cars in general, there's more and more sensors and things like that being included in cars. ABS is something which, again, by law in Europe, every car that's built has to have ABS. Traction control is something else that's very, very common, and these all involve lots of sensors. And so we're seeing this kind of thing combined with telematics, combined with infotainment, being built into cars and resulting in lots of data and lots of connectivity. Now, what does that mean from the point of view of the needs of devices? So if we look at the kind of ideas that we've explored, if we're going to use devices to actually enable us to do these things, what do we need from them in terms of their characteristics? Well, the first is that they need to be available pretty much all the time. If you're going to have an electronic door lock on your house, you really want that available 24/7, don't you? Because you don't want to have to walk up to the house and go, hang on, I'm going to have to reboot the server before I can get into the house. So always on and always available is very important. Same with healthcare, same with motoring. You don't want to have to wait for the system to boot up in order for you to be able to detect things. Because we're talking about lots of devices and lots of data, we're going to have a system that is going to scale. It has to be able to move from a certain number of devices to a huge number of devices without having issues of scalability. It has to perform. That's also very important because despite Moore's law, what we're dealing with here is devices that have a very small footprint. So we're talking about kilobytes, maybe megabytes of memory, but not necessarily gigabytes of memory. Storage is going to be limited. Processing power is going to be limited. So we need something that's going to perform, something that's going to scale. Security is absolutely critical because if we're going to expose all of this type of information, if we're going to have healthcare information being made available, if we're going to have in-car systems, what's the impact of having those systems being hacked? There's lots of write-ups that have been done a little while ago where they were talking about how you could actually interfere with industrial automation systems and cause systems to break by overriding certain security features. So whatever platform we use for this has to be secure. And again, coming back to the in-car systems, what you find right now is that the systems in cars are not secure. There's no level of security built into those that will prevent you from using that system. Now, clearly right now, you actually have to get physical access to the car to be able to do that. So if you want to hack your car, you actually have to plug in something to the service port, and then you can communicate with the car. Once you've plugged in, there's nothing to stop you sending messages to the car. And there's a nice demonstration I saw on YouTube where some people had actually taken, I think it was a Toyota Prius, which had the automatic parking system. So there was a motor that could actually drive the steering wheel and control the steering. And there's somebody sitting in the driver's seat with a Nintendo Game Boy driving the car, because they could actually communicate wirelessly with the car systems and send signals through the buses on the car and be able to drive the car. So they could control the brakes, they could control the steering, acceleration, all of those things. Once we put telematics into that, where you have a modem, you really need some sort of security, because that means that now people have got a wireless way of communicating with the car. If you can hack into that and then access those systems, you're looking at very severe problems if people can do that. But then we also need them to be remotely manageable. That's the idea of, if we've got services that we're making available, what we want to be able to do is enable new services dynamically, and that kind of comes into the platform for new services as well. What we'd like to be able to do, and this is the sort of idea of smart metering, we're measuring electricity, we're measuring usage. How can we then say, okay, the electricity provider wants to add a new service to be able to link that to some other part of the system? So if you're linking it to healthcare maybe, or linking it to the locks on your door, how you can combine these different things into new services. Rather than having somebody go around and deploy those by plugging something in and downloading new code, you want to be able to do it remotely. And then related to that as well is this idea of local intelligence, moving some of the processing away from the server down into the device itself so that it's able to make decisions. If we're gathering huge amounts of data, the problem is that we can overwhelm the server, we can overwhelm the data center by having too much data. We need to be able to filter that at the device level. So we're reading lots of information, and then let's select from that the relevant data and only pass that back to the server, to the data center, so that can be processed. So how does Java fit into that? Well, Java has a number of features which make it ideal for these kinds of activities. Now, if you look at the history of Java, Java goes back 19 years now. And when Java was first developed, it was created really with the idea of embedded devices in mind. There was this thing called the Star 7, which was like the very early iPad, really very, very early iPad. But it was an embedded device, and Java was targeted at that. In 1995, if you think about the typical desktop PC in that time, you were lucky if you had 8 megabytes of memory in your machine. You had something like maybe a 90 megahertz processor, which is very small and very slow by today's standards, but fits very well into the idea of embedded devices, because that's the kind of devices that, or resource footprint that you have for embedded devices today. Java has always been designed with the idea of write once, run anywhere. The virtual machine, the idea of bytecodes that are compiled into native instructions as they're required. In embedded devices, that is very sensible. It really is very well designed for that kind of environment, because embedded devices are not all going to be the same. They won't be using the same processor, they won't be using the same architecture necessarily. So if you can write the same code and have it run on multiple devices without having to do complex porting of that code, you're going to save yourself a lot of time and effort. The fact that lots of people know how to program in Java makes it easy to find developers. Now, I asked who was an embedded developer here, and not many people put their hands up, but I'm assuming that most of you are Java developers. Now, if you're Java developers, it's very easy to take those skills and start becoming an embedded developer. All you need to do is to learn a new set of libraries, which we do for many different things, in terms of understanding how do I talk to a sensor. We'll talk a little bit more about that as we go through. So there's easy ways to become a Java developer. There's easy ways to become an embedded developer. And so a lot of these things make it that Java is a very good platform for these types of devices. And there's other things as well, like the virtualized factor. The fact that the Java virtual machine takes care of memory management for you. It means that you don't have to worry about the sorts of issues that you have with assembler code or C code, C++, where you've got to remember about memory management, you've got to be very careful about using explicit pointers. Java doesn't have that. Implicit pointers means that it's a lot harder in terms of trying to break the system. You know, in C and C++, you can take advantage of buffer overruns as a way of circumventing security. That doesn't happen in Java. So those types of things are very powerful in terms of an argument for why we should use Java in embedded devices. Now, if we look at embedded Java, what we actually have is more than one platform, really. And so you can think of Java SE embedded as being targeted at bigger types of embedded device. And what we're really talking about there is ones that have lots of memory, more than 10 megabytes of memory. So that's, you know, a big device. With that, you can run the full Java SE platform, just the same as you would run on a desktop, just the same as you would run on a laptop, just the same as you would use in a server. So you can use Java SE embedded, exactly the same basic platform as you have with Java SE. If you're looking at smaller devices where you've got less than 10 megabytes of memory, then we have Java ME embedded. And we'll talk more about that as we go through. But the idea that Java Micro Edition, which is the smaller footprint version of the Java platform, will work in much more resource-constrained devices. And then for the very, very bottom end, we have Java Card. I'm not really going to talk about that today. So that will actually work down into the tens of kilobytes of available RAM. But again, that can be used in very much the same way in terms of Java programming. Now, one of the other great things about embedded Java is how easy it is to get started. So who's heard of the Raspberry Pi? Yes, pretty much everybody, I would hope. So the Raspberry Pi is a great development board because it's small and it's cheap. You know, £30 will buy you a Raspberry Pi. Okay, you've got to add a few other bits in terms of the SD card and the power supply and so on. But that will enable you to get started with embedded development. The fact that it has these extra pins on it, which exposes various interfaces that can be used for connecting sensors or motors or any number of different things to that, means that you can get started very quickly with embedded Java development. So what we've done at Oracle is we've actually created specific binaries for the Raspberry Pi. And in terms of Java SE, we've worked with the Raspberry Pi Foundation, and now when you download the Raspbian distribution, you will get the Oracle JDK binary as part of that distribution. You don't even need to download anything extra. But we've also focused on Java ME. Now, with 512 megabytes of memory in this, it's significantly more than you need to run Java ME. But it still works very nicely as a development platform for Java ME types of applications. So you can use Java ME, you can use the pins to connect sensors and so on, and develop your application before moving it onto the actual target platform. In terms of getting started with this, if you go to the Oracle booth outside, we're actually giving away 3 Raspberry Pis each day. So you can enter the prize draw. All you have to do is have your badge scanned, and you've got a chance of winning a Raspberry Pi. So it's even cheaper to get started as an embedded developer. Let's talk about Java ME embedded, the smaller version of Java. Now, when I talk about Java ME, people often sort of think, well, hang on, Java ME, wasn't that when you were doing mobile phones? And it's all about mobile phones and stuff like that. And what's actually happening here is, no, we're not doing mobile phones. I mean, if you look at the mobile phone space, Oracle have accepted that we're not going to play a big part in terms of the use of Java in those devices. So we are targeting our efforts for small things at embedded devices. And that's where Java ME embedded comes in. It's really a shift away from the old ME MEEP, mobile information device profile, which was targeted at the feature phones, to devices which can support these kinds of applications. Now, in terms of Java ME embedded, you can actually squeeze it down into a very small device. So from the actual RAM point of view, the minimum profile set requires about 128 kilobytes of RAM. That's kilobytes, not megabytes, not gigabytes. So that is very, very small. You can go up to the standard profile set, 512K, so half a megabyte. And then if you want the full profile set, then about 2 megabytes of RAM. Now that's RAM for actually running your application. In terms of the libraries and the actual code that you need, again, squeezing it down to the very minimum, you're talking about less than 1 megabyte of like flash memory to store all of the Java virtual machine, Java libraries, and so on. So you can actually squeeze the entire Java runtime, both flash and RAM, into just about 1 megabyte of memory. So 1 megabyte of memory today costs not very much, which means that in this case, you can use Java, as you're familiar with, in very, very small devices. Now, from the point of view of the kind of main features for Java ME embedded, you've got a configurable footprint. So you can change what you use in terms of the different features. It's built for embedded, as I said, so the idea that we're moving away from mobile phones more on types of devices where we're talking to sensors, talking to actuators, and that kind of thing. And we've looked very carefully at the security model. So we've made sure that in terms of the way that you use Java ME embedded, you need to configure the security very carefully in order to access any of the parts of the system. So if you want to access certain pins on like the Raspberry Pi, you have to have the security configured for that. And that means that you can't even bypass security within an application for specific parts of the system. So it does make the security model very tight on that. I would admit it actually makes it harder to develop code because, of course, you're working around the security model, but that's kind of the reality of having a secure system. It should be that way. Now, if we look at the platform overall, there's lots of different bits to it. Realistically, you've got sort of 3 different layers to it. At the bottom, you've got the connected limited device configuration. This is the same way that Java ME has been designed from the beginning, is the idea of having configurations and profiles. So configurations are designed to work for specific resource configurations for devices. So we talk about the amount of memory available, the amount of processing power. So that's your basic virtual machine, the basic set of class libraries that are required to get your application running. On top of that, we have profiles, and then we have some other additional APIs. So we've got the Java ME embedded profile, the Java MEEP, as we call it, version 8. The generic connection framework is already part of Java ME, and we've extended that in terms of Java 8. So I'll talk a little bit more about that as we go through. And another big thing that we've introduced in Java ME 8 is this device I/O API, because moving away from mobile phones and towards embedded devices, we need support for these standards that are used for connecting devices. There's things like GPIO, I2C, SPI. And so that's all covered by the device I/O API. And then on top of that, you've got various other APIs that give you the higher level functions in terms of things like location. So if you want to connect to GPS, in terms of web services. So if you want to either have the device expose a web service or consume a web service, then that's involved there. And so there's various other things around that you can have, but it's all configurable. And that's the really key part about this, is that beyond the sort of the JVM side of things and the CLDC, it's all configurable so that you can add which bits you need for your particular device and for your particular application. Now, in terms of the CLDC, Connected Limited Device Configuration version 8, what we've really tried to do is, as far as possible, align things with what we've done with Java SE 8. So we've moved the language forward a lot. Java ME was one of those things that kind of got a little bit sort of dusty and a little bit abandoned in terms of its development. So we were still using, a very old version of the Java language. So we've really brought that forward. We've introduced a lot of the new features from Java SE 8. We still don't have things like lambdas in there. That will be coming soon, but it's not in CLDC 8. So it is partially aligned, but it's not completely aligned with SE 8. That should be happening as we move forward. Same thing with the VM. So we're aligning with SE 8. So we've introduced things like we now have the invoked dynamic bytecode available, stuff like that. Libraries, again, bringing all the libraries forward, making sure that all the standard libraries that you've got in terms of java.util, java.lang are brought up to date as far as possible with Java SE 8. Compact configuration for very small devices. So again, what we're trying to do here is to reduce the amount of resources that are required based on some work we're doing to minimize the footprint, both by looking at what data structures are used internally, how much space is required for those, maybe making, if we're trying to allocate an array for something, let's make it a small array to start with rather than a bigger one, which will reduce the footprint. Flexible networking through the generic connection framework, I'll talk about that on the next slide, and also making sure that the tooling is available to simplify the process of developing these types of applications, and that comes to NetBeans. So the generic connection framework, this is the way that we do I/O in Java ME. And so rather than having a lot of these different ways of doing input and output and all of the libraries that you have in Java SE, we've tried to provide a simple sort of basic idea of a connection framework and then different types of connections that handle the different interfaces on top of that. And these are a lot of the new things that we've introduced in Java ME 8. So there's things like an HTTP connection now. You've got a modem connection. There's secure datagram connections and all sorts of things like that. So this is a more flexible way of enabling you to connect to different types of things, whether it's through web services, whether it's through a serial line, whether it's over a network or whatever. The mobile embedded profile, as I said, this contains a lot of optional things so that you can decide which particular parts of the specification you want in your application. Because it may be the fact that you don't need media in your application because there is no display. So why would you want to have media? So you can leave that out. If you've got no display, then you don't need the UI part either, so you can leave that out. If you're not working in terms of GPRS and connectivity over a telephone connection, then you don't need the cellular part of things. But you might want to have the idea of software management enabled so that you can dynamically add new services over the network. And that enables you to download a new service, have it run on your device without having to do that actually physically with the device. You can remotely update the services. So a lot of these, like I say, are optional so that you can configure this in the way that you want for your application. I mentioned the device I/O API, and this really is the big new feature in terms of Java ME 8. And like I say, if you look at the Raspberry Pi as a good example, it has all these extra header pins, and they enable you to connect to different types of devices. And there's things like GPIO, general purpose I/O. So you can set the pin high, you can set the pin low, you can read data as a binary value from that pin. There's different types of well-used connection protocols. There's things like I2C, which is the inter something or other communication, I can't remember exactly what it is. SPI as well is a very well-used interface for different types of sensors. So you can connect on a bus, you can have multiple things on that bus, and you can communicate with that from the device I/O API. UART for serial communication. So you can set the baud rate on a particular UART, you can set the parity, you can set the number of bits, all those sorts of things. Good old AT command devices. Now this goes way back to when we used to have modems, but there's still a number of devices that use the AT command set in terms of communication. So we've added part of the API to simplify that for you as well. Analog to digital converters, digital to analog converters, those are supported by the device I/O API, as well as memory mapped I/O. So you can map certain areas of memory in, and then you can effectively do things like peek and poke to set values and retrieve values. There's things like a watchdog timer, there's a pulse counter, so if you want to do have pulses coming in on a particular pin, you can count those pulses. And if you want to control something, like a motor, then there's also the ability to do pulse width modulation generation. So you can actually set up a pulse on a particular pin, have it last for a certain amount of time. And that way you can control the speed on something like a motor. And there's also power management built in, because these types of devices, you typically want to reduce the power consumption as low as possible because they may well be battery powered. So there's various APIs built into this that will allow you to put things into a sleep mode or that kind of thing to manage power. Tooling is very important. So what we've done with NetBeans, okay, so quick show of hands, who's a NetBeans user? Okay, who's an Eclipse user? Okay, what about IntelliJ? Oh, wow, okay, IntelliJ is popular. Well, we like NetBeans, so so we have updated NetBeans because we have the control over that. And so what we've done is we put a lot of facilities into NetBeans in terms of this kind of development. I know Eclipse are also looking at a similar kind of thing. So you've got now the ability to set up emulators, you've got the ability to configure projects for Java ME, and it's very useful, especially in terms of like the security features, because you can say, okay, this is my project, I want to be able to access the GPIO pins, I want to be able to read and write to those GPIO pins. So part of the project, you can set up the security permissions for that project so that it knows exactly what's actually happening, and then the application descriptor is generated for you. Talk about Java SE embedded. So this is, as I say, really the same platform that we're used to in terms of Java SE. From a language point of view, it's exactly the same. And what we've done here is, again, looking at how we can target Java at devices which are going to have less memory, but still enable all of the facilities that you need for certain types of applications. Now, in Java SE 8, we were hoping to get Project Jigsaw into the release, which would enable us to have modularization of the platform. But that didn't actually make it into Java SE 8. It should be in Java SE 9. Hopefully, it will be in Java SE 9. And so what we've done in place of full modularization is introduce the idea of compact profiles. And compact profiles are saying, well, let's take the rt.jar runtime, and let's take a subset of that which is available for specific types of devices or specific types of application. And the compact profile 1, which is the smallest one, requires about 10.4 megabytes of flash memory. So that's quite a lot bigger than the Java ME side of things. But remember that Java SE embedded is targeted at devices which do have more resources. Compact Profile 2 moves up to 15 megabytes. Compact Profile 3 is 20 megabytes. And then the full JRE in terms of just over 4,000 class libraries that we have is about 48 megabytes in size. All of the compact profiles, don't have, or sorry, I should say, none of the compact profiles have any kind of user interface libraries in them. So if you want user interface, then you need the full JRE kind of setup. So again, this is configurable. You can decide which compact profile you want to use. You can determine what you want and then build your runtime accordingly. In terms of what you get for the compact profiles, compact profile 1 is really the minimum set of libraries that you need in order to actually run any kind of application. So even if you wanted to run Hello World, you would need compact profile 1. So it has things like your class loader, your security manager. There's also things like logging is included in there, and even the secure socket layer. From compact profile 2, what we do there is we actually add in things like XML. There's some RMI, which is used in a number of different applications. JDBC is added in there. And that really is, in terms of the migration path, is looking at some of the Java ME pieces and moving that to compact profile 2. Compact profile 3 adds in some management stuff, naming services, even the compiler API. And so that's kind of targeted at applications which require most of the Java SE APIs, but not things like a UI. Then the full Java SE is all of the desktop APIs, things like web services, and for the probably 1 or 2 people who are still using it, Corba. Java SE 8, from a language point of view, hopefully most people are already aware of the new features, but this is kind of like the quick list of what we've added to Java SE 8, and these are all available in Java SE 8 embedded. So Lambda expressions, default methods, annotations on Java types, they're all available. The streams API can be used, the date and time API, and compact profiles. So you get exactly the same feature set that you get with full Java SE, just in an embedded environment. What we've also done is to add some enhancements specifically for the embedded platform. So this is separate from the libraries, separate from the language. This is more about the actual virtual machine and the runtime environment. So there's things like we've added support for Java Flight Recorder. That's what came from the JRocket JVM that was Oracle and BEA before that. So that gives you some very useful profiling tools and the ability to do post-mortem analysis after your application has stopped doing what you wanted it to do. Also, we've looked at how to optimize the VM specifically. So we've done things like reducing the footprint in terms of memory utilization. We've looked at how the JIT works and optimize that specifically for embedded devices. So working on the idea of, reduced memory versus high performance. Obviously, there's a trade-off between those. So you might get slightly less performance than you get with a full JVM on a desktop because of the way the JIT works in terms of reducing memory utilization. Another nice thing, if you've done JNI at all, then you now have the ability to include shared libraries statically into your application. So I know when I've used JNI, that has proved to be something that's quite a challenge, getting all that working. And also, we've done a number of performance improvements specifically around the ARM architecture. Linked to the idea of making the platform smaller and using the custom profiles is the fact that you can now create a custom runtime. And so what you say is, okay, you download the embedded JDK, you select which profile you want, and then you can use this thing called JRE create, which will generate a runtime environment for you with just the pieces that you're actually interested in. And the way that you do that is with a command like this, where you're saying, okay, JRE create.shell, destination is where you want the JRE to live, and then you say, okay, I'm going to use a profile which is compact 2. You've got a choice of the way that the JVM is configured. So you can either say minimal, which is the lowest footprint in terms of memory. You can say client, which is tuned for the responsiveness, so that will give you better response times. Or server, which is tuned for longer running applications, because clearly you're going to understand what the profile of your application is. So you could specify that on the command line. You can also say that you want to keep all the debug information, because again, if you're trying to make it smaller, stripping out debug information will reduce the size of the footprint. Supported hardware platforms for Java SE 8 embedded. We cover a wide range of ARM architectures. So we do cover ARM v7, ARM v6, even ARM v5. Really the differences between those are how we handle floating point arithmetic. So ARM v5 is all about soft floating point, so it uses libraries. ARM v6 and v7 can use the virtual floating point stuff, which is part of the ARM architecture, and then ARM v7 can use also hard floating point, which is where you've actually got the hardware built into the chip as well. Also support power architecture, so the E600 or the E500 on Linux, and we also have a version for x86 on Linux. So, you know, Intel have come out with some small boards like the Raspberry Pi recently as well. JavaFX. JavaFX is what we did a few years ago in terms of a replacement for Swing for developing user interface applications. Now, it's not part of the SE standard, but we ship it with the Oracle JDK and the JRE. And we've also targeted this specifically at embedded devices as well. So we've done a lot of work in terms of tuning that. So there's things like we've worked very carefully with the acceleration using GPU, because the embedded Java run, or Java SE embedded runs on top of Linux most of the time. We use OpenGLE as the way that we implement that. It works directly to the frame buffer. So we don't support X Windows. You can't run a JavaFX application as a separate application from the desktop, but we don't see that as a problem because most people are not doing that for embedded devices. They want to talk direct to the frame buffer and have the whole display taken over by the application. If you have a system that doesn't have a GPU, then we also have a software fallback, so we can do the rendering in software only without using the GPU. Integrated window management, integrated virtual keyboard, those are all available. And then in terms of the differences between JavaFX on the desktop and JavaFX on embedded devices, there's a couple of things that we don't support. So, for example, the media engine is not supported. There is actually a way of getting around that, so you can use the native media playback system, and then you just put an invisible window on top of it, and it just plays from underneath. WebNode is not on there. That's a size constraint because we use the WebKit rendering engine, and that's about half the size of the Java runtime. 3D graphics support is not in there at the moment, and also Swing and SWT integration is not there either. Just a couple of things to bear in mind when you're doing JavaFX on an embedded device. Big scene graphs, which is what you use in terms of defining the layout of your components, are not great on embedded devices, so try and keep things as simple as possible. Ideally keep the number of nodes to a minimum, because the more nodes you have, the more processing, the more memory is taken. And you can use certain techniques in terms of building your scene graph ahead of time, but that again is a trade-off between memory and the amount of time you've got. This is just an example of a touchscreen that I used for a particular application. Bought it off eBay. It was actually pretty simple to integrate with the Raspberry Pi and using Java SE embedded and JavaFX. So I was able to have a touchscreen where I could control my application from that. Just used a USB, and it was pretty straightforward. Tools for Java SE 8 embedded. Again, NetBeans. We've made changes to that. So what we've tried to do there is to simplify the process in terms of deployment. So now you can actually link to something like a Raspberry Pi, and you can do one-click deploy from your laptop to the Raspberry Pi in terms of doing testing. You can also do remote debugging and things like that. Just a little bit about future directions. One of the things we've done recently is actually open source the Device I/O API, and we're currently working on making that available for Java SE embedded as well as Java ME embedded, and that will be a very useful thing to do. So if you're interested in that, there's a wiki page on the OpenJDK project that you can go to, and you can see what we're doing there. We've also just recently announced that we're doing a MIPS port of Java embedded. So we're working with the company Imagination Technologies, who basically own the MIPS architecture now. Initially, we're doing MIPS R2, and then we'll also be working on MIPS R5. So that extends the range of processors that we're covering. And that really sort of is exactly what I was saying earlier about the fact that Java has a great advantage because you can take the same code and you can run it on an ARM processor, you can run it on a PowerPC processor, an Intel processor, and soon a MIPS processor. And it's the same code base that you're using. You don't have to do any extensive porting for that. So in terms of IoT, Java does address many of the challenges, things like portability. Security is built in from the very beginning with Java. You've got this idea of, the sandbox. You've got this idea of signed applications, all of those sorts of things. Developer skills are available because lots of people know how to program in Java. Scalable platform, as I say, right from like 100K of RAM for Java ME embedded, 8 megabytes of RAM for Java SE embedded, and then JavaFX for user interfaces. So that is pretty much it, and I think I'm just about on time. So I don't know if, because I've run out of time, if anybody's got any questions, I'll be on the Oracle booth, and you can come up and find me there, and we can chat about things after that. And yes, please do give your feedback. I know one person already did that before I even started talking, which was quite impressive. So yes, please do give your feedback on the presentation. I hope you enjoyed it. Thank you very much.